Okay, we're having a look at numerical methods. So I've got a few videos to do on numerical methods, and this is going to be the first one. Just a bit of an introduction as to what they are, why they're used, and have a look at bounds. So numerical methods, there's lots of different numerical methods for a variety of different things, but on this course, on the A-level course, we only look at numerical methods to solve equations. So numerical methods to solve equations. Not every equation can be analytically solved, that is, you cannot necessarily make the unknown the subject. For example, if I have e to the x plus sine of x equals 0, how do I go about finding x values which satisfy this equation? You can't make x the subject, so we resort to non-analytical techniques, which is numerical methods. So this is exactly why we have to employ numerical methods when we have equations that can't be solved. Okay, so on this course we look at two numerical methods in particular. We look at the rearrangement method and we also look at the Newton-Raphson method. Newton-Raphson, R-A-P-H-S-O-N, Newton-Raphson method. And both of these are a method of fixed point iteration. What that means is when you come to actually execute the methods, you will have the next approximation is some function, let's call it a, of the previous approximation. And as you progress through the approximations, the values will either converge onto the correct root, or the method will fail and it will diverge away to infinity. Okay, so we're going to have videos on each of these to come. Okay, so going back to this, well, let's consider when x is, in fact, let's consider the graphs. So let's consider first of all y equals e to the x, and let's also consider the graph y equals minus sine of x. Now, y equals e to the x is the exponential graph that goes through the number 1 on the y-axis, and this sine graph here is the negative of the sine graph. So the sine graph would usually start at the origin and go up, but this is going to start at the origin and come down, and it's just going to follow the sine wave over there, and it's going to come and do the sine wave that way. So what we've got here is we've got this point here, which is an intersection of these two curves. And this value of x, where this happens, we tend to refer to as alpha, and we tend to use the Greek alphabet to refer to our unknown roots, alpha, beta, gamma, etc. So if we were to find the value of alpha, then you would set the y's to be equal to each other. So that would be e to the x equals minus sine of x. Rearrange that, that's going to give us e to the x plus sine of x equals 0. Okay. Now this equation we can see has a root that's slightly less than 1. And in fact, if I plug in f of minus 1, sorry, slightly less than 0, and f of 0, where f is the function equals 0 is what I'm trying to solve, then I'm looking for a sign change. So I calculate e, if I can find my e, there he is, e to the power minus 1 plus sine of minus 1, and I'm in radians for this, I get minus 0.474. I mean, it doesn't overly matter, it's the sign that I'm interested in, it's negative. And if I plug in x is 0, I'm going to get 1 plus 0, which is 1. So because there's a sign change, i.e. it's gone from negative to positive, it means there's a root in between them. So if I have a situation where f of, let's say, a is negative, and f of b is positive, and f is continuous on AB, I'll come back to that, what that means in a minute, then that implies that there's a root, there's at least to f of x equals 0 in the interval AB. And that has to be true. Not necessarily true the other way, but definitely true from left to right. Let's try and illustrate that to try and get you to see why it's true. I'm assuming that A is less than B, but it could be that A is more than B. Okay, so I've got A and B there. And if f of A is negative, that means that the curve at this point is going to be below the x-axis. This is my x-axis here. And if f of b is positive, that means the curve at this point is going to be above the x-axis there. Now, if this curve is continuous, if f is continuous, then for the curve to get from this point here to this point here, it has to cross this line here. You can't go back on yourself because it's not a function if it does that. And it can't just jump, because that's what it means to be continuous. It means there's no breaks in the line. So if I've got a sign change between two x values for f, then that means that there must be at least one root inside that interval. So there could be more than one. I could end up doing that. It could be 3 roots, or it could do that. In this case, there's one root, but there has to be at least one root, and that's the key point. There has to be at least one root to f of x equals 0. That is an x-intercept in the interval a to b. Okay, that's exactly what all this means. So we take advantage of this property to check, to make sure our answers make sense and are still containing our root. Okay. So let's have a look at an example. Example 1. Show that e to the x equals 5x has a root in the interval 0, 1. So first of all, before we kind of dive into that, we need to rearrange it to make it f of x equals 0. So I'm going to say let f of x equal e to the x minus 5x. And I want that to be 0 so that alpha, the root of this equation, will satisfy this equation. Okay, but I'm defining f of x to be this, and that means now if I were to plot this function, e to the x minus 5x, on a graph, then where it crosses the x-axis, those are the places that my roots are at. Okay, so in the interval 0 to 1, it's a continuous function. Okay, e is continuous and a linear function is continuous. In fact, any polynomial is continuous. Sine and cos, they're both continuous. Tan is not, however, just be careful with that. And yeah, you know that e is continuous. Logs are continuous as well. So we're going to calculate f of 0, and that's going to come out to be 1 minus 0, which is 1, so that's positive. And f of 1, that's going to become e minus 5. I mean, I know that's negative because e is about 2.7. So if I subtract 5 from it, I'm definitely less than 0. So the point is there's a change of sign, and that's exactly the phraseology we're going to use. There's a change of sign. Therefore, there exists, which in maths is a big capital E backwards, there exists a root in the interval 0, 1. Okay. Might be more than 1, but there's definitely one root between 0 and 1. Part B, show that the root is 0.259 to 3 decimal places. Well, what we're going to do to prove that this is true, and these are types of questions that can come up, is we are going to look at the bounds of every single number that rounds to that. So the lowest number possible that will round to this, to 3 decimal places, is 0.2585. The best thing to do is just to drop the last number down to the next integer and then pop a 5 on the end. that must be less than or equal to the root, which I'm going to call alpha. And then the upper bound is going to be 0.2595. You just pop a 5 on the end, and that will give you the upper bound. Now, every single number in this interval rounds to that number to 3 decimal places. Every single number. Even though there's an infinite number of numbers in there, we know that all of them round to that. So if alpha lies in this interval, then that means that alpha is 0.259 to 3 decimal places. So I'm going to do exactly the same as I did in part A, except instead of using 0 and 1, I'm going to use these two new bounds of 0.2585 and 0.2595. And again, we can use the table mode if you want to. I'm actually just not going to bother this time. So it's going to be e to the 0.2585 minus 5 times 0.2585. So that gives me 0.002. Again, I don't care about the number, I care about the sign. That is positive. Okay, that's the sign of it, it's a positive number. And if I change that 8 for a 9, I'm hoping it will come out to be negative. It does. It's minus 0.001, which is less than 0. So because there is a change of sign between these two bounds, it means alpha lies in that interval. So alpha is an element of the interval 0.2585, 0.2595. Therefore, alpha equals 0.259 to 3 decimal places. That proves it. Well, that and the fact that f is continuous. But actually on this course, you don't need to argue that too much. Okay. Example number 2. Explain why tan of x minus x doesn't have a root in the interval 1 to 2, even though tan of 1 minus 1 is positive and tan of 2 minus 2 is negative. Let's just check that. If I do tan of 1 minus 1, that is indeed a positive number, and tan of 2 minus 2, that is indeed a negative number. Why is this not continuous? Well, let's just have a look at these two functions. I say two functions. Let's plot y equals tan of x and y equals x, which is essentially what I'm looking for here. Solutions to when these two graphs intersect. Okay, that would satisfy this equation. Okay, add the x to both sides and then say y equals tan x, y equals x. So let's have a look at tan. We're looking really just between 1 and 2, but we've got this, and then there's an asymptote there, and then we got that, and then we got that, and there's an asymptote there. That's pi. That's now at 3, and that's pi on 2, so that's about 1.7-ish. There's my x-axis. There's my tan curve, so that's tan x. And then my y equals x curve, that's actually a tangent at this point, so it does go through the origin. There's that. There's y equals x. It will have solutions. There are solutions to this. If I continue this curve up, maybe not there, but in fact, yeah, definitely there. Then this will cross that point. So there will be an alpha over here somewhere. That is much bigger than 2, because it's bigger than pi. Why isn't there one between 1 and 2? Well, let's look at this. Here, the blue curve is above the pink curve at the number 1. And at the number 2, the blue curve is below the pink curve, which means there should have been a root. What's happened instead is there's been a discontinuity in tan of x. So the reason why it doesn't have a root is because tan of x is not continuous on the interval 1, 2. Okay, it's because of that asymptote at x equals pi on 2. That's what makes the blue curve jump the other side of the pink curve. It doesn't actually cross the pink curve at all. It just jumps because of the asymptote. So that's why it doesn't have a root, even though this says it should. Okay, it's because it's not continuous. So they don't really try and trick you up with questions like this on the A-level papers. They tend to be continuous functions, but it is something worth bearing in mind because this does actually rely on f being continuous. Okay, this process. Okay. That's an introduction. My next video will be on the rearrangement method, and then I'll be doing a video on the Newton-Raphson method as well. Thanks for watching.